Hello. So for today's content review session, I plan on going over um chapter 11, 12, and 13 reactions. For chapter 11 and 12 are alkene reactions. Chapter 13 is the alkyne reaction. Practice problems connect those concepts together. And after that, are going to go over any questions you guys have and then start on the new chapter, the conjugated systems, chapter 14. So first, let's get started on an example problem here. Let's say we have a multi-step synthesis like this, where this multi-step synthesis here is going to combine alkene and alkyne reactions together, right? Where let's say the first reaction we are going to do is NaNH2, 3 equivalents of it. The second step, let's say H2O. Third step, NaNH2. Fourth step, this haloalkane. And then the fifth step, let's say H2 Lindlar's catalyst. Okay. So work on this for like around 3 to 4 minutes, and I will get back to this problem. And I'm going to add someone in the canvas. Okay. Okay. Okay, so we have vicinal dihalide here at the end of the molecule, where what do you guys think is going to happen after the
اه
first
يشيل
two
والله ما
reactions here?
بشوفه.
We have three equivalents of NaNH2 and second step of water. What do you guys think that is going to do to this vicinal dihalide here? We have a strong base and two good leaving groups. What reaction comes to mind? So whenever we have a strong base and a good leaving group, that reaction is going to be elimination reaction, E2 reaction. So we're going to do elimination 2 times, where let's say the first equivalent of NH2 minus comes in, grabs that hydrogen right there, makes a double bond there, and kicks out that leaving group. That would make that alkene right there. We have another equivalence and another good leaving group here. So we're going to do this reaction one more time. We are going to bring in the second equivalence of the strong base NH2 minus, grab that beta hydrogen, form the triple bond there, kick out that leaving group there. This will form our triple bond here. But we know that the bond angle for triple bonds are 180 degrees, which is why I made that linear. Where the third equivalence of the strong base is going to deprotonate that terminal alkyne to give us this alkyne anion here, where there's a negative charge on that carbon right there that got deprotonated. right? Now, the second step, it could be H2O or H3O plus or H2SO4. That is going to protonate the alkyne anion here and give us this terminal alkyne here, right? Where the next step, NaNH2, is going to just deprotonate that terminal alkyne and give us this alkyne anion here, where this alkyne anion here can be a nucleophile or a base because it is negatively charged. When we bring in the fourth step, that halo alkane here, that is primary because that carbon there is attached to only one other carbon, an SN2 reaction is going to happen where this nucleophile here attacks that partial positive carbon and kicks out the leaving group. Let's star the attacking atom and let's dot the atom being attacked. This is the starred atom. This is the dot atom right there. Now, let's make the new connection between the star and dot atom. This is the star atom here. This is the dot atom right there. This is the new bond that is formed between the star and dot atom after the SN2 reaction. Now let's draw what is attached to the dot atom. The dot atom here is attached to that ethyl group. So we are going to draw that ethyl group right there. This is the product after the SN2 reaction here. Now, this is the new reaction that you guys are learning about. Everything up until this point is, oh, actually new reaction, yeah, because this is formation of terminal alkyne, which is the new reaction post midterm one. Yeah, all of these reactions except the SN2 are like post midterm one material. The H2 Lindlar's catalyst is a reducing agent that would reduce that alkyne into a cis alkene. Right. So to keep track of all the carbons, I like to number my alkyne. So let's say this is 1, 2, 3, 4, 5, 6, 7, 8 carbons. I know there's going to be a cis double bond between carbons 4 and 5. So when I draw out my product, that's 2, 3, 4, and the next one, 5 right there. There's a cis double bond right there. So I have to draw it in a way that that double bond is cis. 1, 2, 3, 4, 5, 6, 7, 8, like that. The final answer. Okay, so this could have been a synthesis problem where he did not give you those reactions. He just gives you that reacted molecule and this product molecule, and then you have to figure out the reactions it took to get there, right? But this is multi-step predicted product where you have to predict the product after all these reactions. Okay. Let's do one more practice problem on alkene and alkynes and then move on to the next chapter to conjugated systems. But this time let's do a synthesis problem. Let's say we have this terminal alkyne and we want to make, say, this product here, where this is just plus the enantiomer. Okay. Okay. So tip for synthesis problem is to look at what is the similarity between the reactant molecule and the product molecule. I'm going to say that this main backbone chain right here is this part of the product molecule here, right? Because let's say this is the cyclopentane ring right there, and out of that cyclopentane ring, we have two carbons coming out of it, which are these two carbons right here, right? The new stuff that we added are these two alcohols and that R group right there. Okay, we could go backwards here. A reaction we know that adds two alcohols vicinal or adjacent to each other on the same side, syn addition, is dihydroxylation, where the reagents are OSO4, osmium tetroxide, and reducing agent. That would have to come from a double bond between the carbons holding those alcohols. So going backwards here, which is retrosynthesis, we could say that that product molecule came from this double bond right here, right? And then we also see that this double bond right here is a trans alkene, where that trans alkene could have came from the alkyne, from the original molecule here. Where let's say that that is the alkyne right there, and we have 1, 2, 3 carbons coming out of that alkyne, right? The reducing agent that converts an alkyne into a trans alkene is going to be sodium metal, at least two equivalents of it in ammonia liquid, right? Now we have to figure out a way on how to add this extra R group on this terminal alkyne here. We know that we added an extra carbon-carbon group, which back in 1A, the reaction that does that are Grignard reagents or reactions. But in this alkyne chapter, there's another way. We could make this terminal alkyne nucleophilic here by giving it a negative charge. And if that's nucleophilic, then that means that this carbon here had to be electrophilic. To make this terminal alkyne carbon negatively charged, we can deprotonate the terminal alkyne hydrogen with a strong base like NaNH2. That is going to give that alkyne a negative charge here, which is our nucleophile, right? We want to add this R group here, where we want this dotted carbon to be positively charged. To make that dotted carbon positively charged, we have to attach it to an electronegative atom that is also a good leaving group. We could attach that to bromine, chlorine, iodine, OMS, OTS, OTF, any good leaving group, right? Where this is the dot carbon right there, where this nucleophile is just going to attack that electrophile, kick out that bromine for SN2 reaction, and give us this extended alkyne. From there, we reduce that to the trans alkene using sodium metal, two equivalents of it in ammonia liquid. And then we do dihydroxylation to give us this syn vicinal diol, where the alcohols are on adjacent sides of each other on the same side, right? So these are reactions that connect the alkene and alkyne reactions together. Where I know Pascal's synthesis problems are like 2 to 3 steps, but if you understand this, then I think you should be prepared for the Pascal's exams. It's synthesis problem, but the vocab is a different story. So now let's move on to chapter 14, which are going to be conjugated systems. Or we could say delocalized pi systems. There's going to be a lot of resonance in this chapter. Delocalized pi systems. Well, first, do you guys have any questions on the alkene and alkyne chapter or what we went over so far? Okay, so let's move on to the next chapter, chapter 14. So A system is going to be delocalized if there are at least 3 p orbitals adjacent to each other. So an example of that would be something like this. Say we have this structure here where we have sp2 carbons here, here, and here. Since these are sp2 carbons, we know that all of these carbons have p orbitals. When you have a network of at least 3 p orbitals next to each other, that is going to have resonance and delocalization, delocalization, right? Where we know that since there's a carbocation here, we could do resonance by shifting this double bond there. When we draw that resonance structure, it should look like this. Delocalization would increase stability of a molecule because it increases resonance, right? Where the things that could do resonance are carbocations, carb anions, and radicals, right? Can do resonance. So this example that I just showed you here is an example of a carbocation doing resonance. Now, a carb anion is a carbon having an anion, a negative charge with a lone pair of electrons. This can also do resonance, but the thing that is going to move first is that lone pair of electrons right there, which is going to make a double bond here. And oh shoot, I just see the chat. What is the purpose of deprotonating a terminal alkyne and protonating it again with water and then deprotonating it again with another NH2? Yeah, so when I made this problem, I just realized that we didn't need this protonation step. We could have just or this deprotonation step, we could have just went straight to the SN2 reaction there. So this was kind of like useless, but I just wanted to include it there to include more reactions. But we didn't need those 2 steps to get to the same exact structure here, right? Because the NH2 3 equivalents could have just stopped here, and then you could have just went straight with this haloalkane to get that, and then reduce that there. We didn't need these 2 steps here, right? Yeah, it's just to show the different reactions. Where the first 2 steps made the terminal alkyne. The third step deprotonates that terminal alkyne to make the alkynyl anion. The fourth step makes the SN2 reaction. And then the last step reduces that alkyne into the cis alkene. Yeah. Right. So this is a carb anion here that can do resonance like that, where we moved that lone pair of electrons to make a double bond here. And this double bond would move onto that carbon right there, where we know that bond represents 2 electrons, and those 2 electrons are going to move onto that carbon, giving that carbon a negative charge there. Right. So another thing that could do resonance are radicals or 1 electrons. When we draw the movement of 1 electrons, we draw single hook arrows. So the resonance of this would look like this. That radical moves there. One of the electrons of this bond makes a double bond with that radical here. The other electron goes to make a radical on the other carbon, giving us this resonance structure here. where we see that in all cases, the carbocation, the carb anion, and the radical, they are delocalized because they are doing resonance between at least three atoms. 1, 2, 3, 1, 2, 3, 1, 2, 3. Right? And that increases the stability of the molecule because it increases resonance. Yeah. Okay, let's go over now allylic reactions, radical halogenation. Okay. So let's say we have this alkene right here. We know that in the alkene chapter, if we put that through Br2 by itself or in a non-nucleophilic solvent like CCl4, that is going to add bromines on both carbons of the alkene and tie to each other like that, right? But let's say we wanted to add the bromine on this carbon right here, where that carbon right there, right next to the alkene, is called the allylic carbon. That's just a position term to show where that carbon is. Allylic meaning one carbon away from a double bonded carbon, right? One way that you could do that is to put Br2 in low concentration and put that under roar or light. And that is going to give you that bromine attached to that allylic carbon right there. This right here has to be in low concentration because if you had high concentration, then you would get this product here. It would just go through the first reaction. A better way to do this without worrying about the concentration is to use NBS under light, right? Where that NBS is going to add a bromine on the allylic position here, right? So this could be useful for synthesis. If you used, let's say, NCS, then you would add a chlorine on the allylic position instead of a bromine. Right. NBS stands for N-bromo succinimide. Right, let me just make sure, just in case. NBS. N-bromo succinimide. Okay, succinimide, not succinimide, succinimide. Succinimide. Right. Where that NBS looks like this. The N is the nitrogen attached to the bromine with this R group here with two carbonyls. Okay, let's see. I think Pascal didn't go over this reaction yet, so I'm not sure if you need to know the mechanism, but let's just go over it just in case. The mechanism of this reaction that adds the bromine to the allylic position with NBS is this right here. Let's draw out the NBS here. The first step is that that carbonyl is going to get protonated by HBr floating around. Right? The HBr comes with the NBS. That carbonyl oxygen grabs the hydrogen, kicks out the Br, and gives us this protonated carbonyl oxygen here. where we see that this protonated NBS structure can do resonance by moving this lone pair of electrons on nitrogen to make a double bond there and pop that double bond onto that oxygen right there. That would give us this resonance structure here. Right? And I don't think this mechanism will be tested, like it's hydroversion oxidation, but let's just go over it just in case. Where this is the resonance structure of that protonated carbonyl, where now the positive charge is on this nitrogen. Right? The Br minus that got kicked out is going to come back and attack that bromine right there, attached to that positive charged nitrogen. Then that bond between nitrogen and bromine is going to go onto that nitrogen and give us this intermediate here. A neutral nitrogen with a lone pair now. And when this Br attacked that Br, we created Br2, which looks like that, right? Where from this Br2 here, we could do an initiation step-like reaction where we form two Br radicals because we are under light. That's going to give us two bromine radicals there. Now we could bring in our alkene structure here, right? Where at the allylic position, let's draw out all of the carbons at the allylic position there. This bromine radical here is going to react with one of the hydrogens at the allylic position, and one of the electrons here of that bond is going to make a radical on that allylic position there, right? And that gives us that radical right there on the allylic carbon. Okay. So we know that this allylic radical here can do resonance with that double bond right there. It's like the exact same resonance structure I showed you guys here, where we could make a double bond with that other double bond and make the radical move there. When we do that, we get a double bond here and a radical there, right? Okay. So we know that this double bond right here is more stable than this double bond because this is a di-substituted double bond. This is a mono-substituted double bond. This intermediate here will give us the thermodynamic product. And this here will give us the kinetic product. And this concept here is important for future reactions. Let me make that more clear on the next page. So a thermodynamic product will give you a more stable product, which could be in the form of alkene, more stable alkene. Right? Kinetic product will come from the most stable intermediate. Most stable intermediate. Like a carbocation intermediate or a radical intermediate, right? The reason why this is the kinetic product is because this radical right here on that structure is secondary allylic, whereas this radical here is primary allylic. Secondary allylic is more stable than primary allylic, which is why it gives us the kinetic product. But This double bond here is less stable than that double bond, which is why it's not the thermodynamic product. This is the thermodynamic product because it gives us the more stable double bond. Okay. Where now we could just, let's say, bring in those two resin structures together and then bring in Br2s. These radicals here are just going to bond with one of the Brs, kicking out another Br radical, which will propagate the reaction. Right? Where we said this right here is the major product because it is the thermodynamic product. This is the minor product because it is the kinetic product. This is the more stable double bond. This is the less stable double bond. But we get a mix of these two products. But for predicted product, just write the major products here. The one, or actually, no, yeah, write both products because last quarter, Helix wanted to test you on both the thermodynamic and kinetic products, but I don't know about Pascal, so we'll see. The next reaction, any questions on this reaction? Right, where this NBS reaction here, it's most likely going to be tested on predicted products. So, did you say the thermodynamic product is always major? For NBS, yes, the thermodynamic product is always going to be major. In the future reactions we learn, the thermodynamic product is always going to be major if we have high temperature, high heat. And the kinetic product will be the major product if we are in low temperature, low heat. So, and different professors use different temperatures. We'll just have to wait and see what Pascal says about the temperature and when the thermodynamic product is favored over the kinetic product and when the kinetic product is favored over the thermodynamic product. But it just depends on the temperature on which product is more stable in the major one. Right. Could you just go to the thermodynamic? Yeah. Thermodynamic product gives us the more stable product, like the alkene. Kinetic product will come from the more stable carbocation intermediate or the more stable radical intermediate. Right. So let's do some practice NBS questions and predict the products and then move on to the next reaction. Okay, so say we have okay, this is a good one. That alkene, put that through NBS and light. So when we see this alkene here with NBS and light, the first thing you do is look at your allylic positions. Locate your allylic carbons. The allylic carbons could either be here or here, right? The next thing you do is figure out which allylic carbon will give you your more stable carbocation. This allylic carbon here is more substituted, so it will give us the more stable radical. So somewhere in the mechanism, we have that radical right there, tertiary allylic radical. Right. After a few steps, and the mechanism that I went over is over here, right? Where it will add a radical on the allylic carbons. The reason why I put a radical on this allylic carbon instead of this one is because this one is more stable. Now, from here, once we figured out the most stable radical, we do the resonance structure of that radical, which gives us that radical right there, right? Based on these resonance structures, let's say this is A, this is B. Which one will give us the thermodynamic product? Yeah, so carbons are let me go over that again, where the definition of allylic and the position terms, right? So position terms. It's just like a terminology vocab thing, position terms. Let's say we have this alkene right here. The carbons that are part of the double bond directly are vinylic. The carbons that are one away from the double bonded carbons are allylic. And let's say we had a triple bond somewhere, like this. The carbons that are, see, let me make sure this is right. Yeah. Okay. Yeah. So the ones that are next to the alkyne right here, not on the alkyne, but next to it, are propylic. The carbons on the double bond, vinylic. Carbons next to the double bond, allylic. Carbons next to the alkyne, propylic. So whenever you see NBS, always think of allylic bromination, where you're going to add a bromine group at the allylic carbon, right? But first, there are like different allylic carbons you could get. We see that these two are our allylic carbons because they are one away from the double bond. We know that this one here will give us the more stable allylic radical because it is more substituted, which is why I drew out that allylic radical instead of this allylic radical here, because that is less stable than this, right? Allylic only refer to one carbon away from double bond. Allylic. Yes, allylic will refer to one away from a double bond. You could also have something like this where this carbon right here is one away from this double bond right here, but that double bond is also part of a benzene ring. If it's part of a benzene ring, that is benzylic, which is gonna be chapter 15, the chapter after this one, the benzenes. Right. But for now, we're just focused on the allylic carbons for this NBS reaction. Why are there two arrows on the first step? Oh, yeah. So this right here, I just drew out multiple arrows because this radical here does not come from one step. That radical comes from multiple steps, which are these right here. But I highly doubt that that's going to be tested on the exam, just like the hydroboration oxidation mechanism, which was the really long one, weird one. It's more probably going to be like the HXX2 mechanism, right? The most important thing here to know about NBS is that at the allylic carbon, you're going to add a bromine, right? So the first step, look for your most stable allylic carbon. That will give you your most stable radical, which is this one here. Once we figure that out, we draw out its resonance structure, which is this right here. Now, one of these resonance structures is going to give us the thermodynamic product, and one of it is going to give us the kinetic product. We said that the thermodynamic product gives us the more stable double bond. This double bond here is tri-substituted, whereas this double bond here is di-substituted. Since this is a more stable double bond, this intermediate here will give us the thermodynamic product. Right. For kinetic product, we said that it comes from the more stable intermediate. This radical here is tertiary allylic, and this radical here is secondary allylic. Since this radical here is more stable, this intermediate will give us the kinetic product, right? Where whenever you see the radical there, just add just add a bromine there, right? So bromine, that's one of the products. The other product is going to be this right here, right? Where this is the thermodynamic product, and this is the kinetic product here. Yeah, these are your two separate answers there. Thermo meaning that we have a more stable double bond. Kinetic meaning that this bromine came from the more stable radical, more stable intermediate. Okay, so any questions on this NBS reaction? Okay, let's move on to the next reaction, which is going to be nucleophilic substitution, like SN2 or SN1, substitution of allylic halide. Okay. So in 118A, let's say we have this primary substrate and we try to react that with H2O. This is a primary substrate here, and water is a weak base, weak nucleophile. Right. So we can't do SN2 here because this is not a strong nucleophile. SN2 reagents would require a strong nucleophile and a weak base such as CN minus, Cl minus, Br minus, I minus, everything else, N3 minus, right? But if you have water or alcohol, those are weak bases, weak nucleophiles, which favors SN1 E1 reactions. Where we know that for SN1 E1 reactions, the intermediate is a carbocation. Because for SN1 and E1 reactions, the very first step of the mechanism is that the leaving group leaves and form a carbocation. But since we have a primary leaving group, when that leaving group leaves first, we are going to form this primary carbocation here, which is not stable, unstable. So we are not going to form that at all. This is no reaction. Right? Does that make sense so far? So this is just a review of 118A, like the SN2, SN1, E1, E2 reactions. This is no reaction because we can't make a primary carbocation, and we have a weak base, strong nucleophile. This is like where you use the magic table to determine what kind of reaction it is, or like if it's SN2, SN1, E1, or if there's no reaction. But this is the reason why it's no reaction here, because of an unstable carbocation. Right? But now with the new material, let's say we have an allylic halide that is still primary. So let's say we have the same kind of structure, but now it is allylic, because this carbon here is an allylic carbon because it is one away from this double bond here, right? And let's try to react it with a weak base, weak nucleophile like water again. Now there will be reaction because there would be an SN1E1 reaction where the leaving group can leave by itself now. It will leave and form this carbocation right here. This is now stabilized by that double bond right there because it could do resonance. When it could do resonance, it is more stable like that, right? Before, when we made that leaving group leave, this carbocation here cannot do any resonance at all, which is why it is really unstable. But this carbocation right here, even though it's primary, this is a primary allylic carbocation. Whereas this one here is just a primary carbocation, not allylic. No resonance. Whereas this one does have resonance, which makes it more stable. Right. Okay, where now we could apply the same concept of thermodynamic and kinetic product. We said that the thermodynamic product gives us the more stable double bond, which is this resonance structure here. That's going to give us the thermodynamic product. The kinetic product, we said that that will come from the more stable carbocation or more stable intermediate, where the intermediate could be a carbocation or radical. This is the more stable intermediate here because it's secondary allylic, which is why this is going to give us the kinetic product. So let's say we bring in our water molecule. And it attacks that carbocation like that. Let's look at the purple arrow first. Okay. When this oxygen of the water attacks that carbon, we get this intermediate where we could use another water to deprotonate it, make it neutral, alcohol like that. This is our thermodynamic product. Now, if we look at the pink arrow, when the water attacked that carbocation, we get this intermediate. We could neutralize that by bringing in another water and give us this thermodynamic kinetic product. Kinetic product. This is kinetic product because it came from the more stable intermediate. Right? And your answer will depend on the temperature he gives you. Right? If you have high temperature, then your thermodynamic product would be major. If you have low temperature or low heat, your kinetic product would be major. And we'll just have to wait to see if what Pascal says, like what temperature is going to be thermodynamic above what degree and below what degree is kinetic. For the stereochemistry of these, here, this is an SN1 reaction where this carbocation is sp2 flat and planar. When the water attacks, it could attack on the top or bottom side, making this wedge or dash. So you could include stereochemistry like that, but since there are no other Carl centers, if we make that into a flat bond, this flat bond here represents that it could either be a wedge or a dash. But in this product here, we do not need to include stereochemistry at all because this is not a chiral center. That carbon there has two hydrogens. So if that's not a chiral center, we don't have to worry about stereochemistry. But this right here is a chiral center. So there technically is stereochemistry there, wedge or dash, but it could either be wedge or dash because when the water attacks, it attacks a flat carbocation, where it has the option to attack on the top side giving you the wedge product, or the backside, giving you the dash product. Yeah. Okay, let's try an example problem here. Let's try this and then move on to the next reaction. Okay, take 1 to 2 minutes to try this, or actually, yeah, 2 to 3 minutes to try this. And also, label your product as either thermodynamic or kinetic, because we're gonna get two different products depending on the temperature. Okay, so for this problem here, this is our substrate because that is the one holding the leaving group. That is tertiary allylic. Not just a tertiary substrate, it is also allylic because it is one away from the double bond here. We have ETOH, which is ethanol. ET meaning two carbons, where any neutral ROH is a weak base, weak nucleophile. Big sign of SN1 E1 reaction, where the first step of this mechanism, kick out that good leaving group, form your carbocation there. We know that this carbocation here is allylic, meaning that it is one away from this double bond, which means that it can do resonance. So let's draw out that resonance structure here. Once we have that resonance structure, now this is the part where we determine which intermediate will give us the thermodynamic product and which intermediate will give us the kinetic product. Thermodynamic is the one that gives us the more stable double bond. So this intermediate here gives us the thermodynamic product, because this double bond here is tri-substituted, 1, 2, 3, whereas this double bond here is mono substituted, right? And this intermediate here will give us the kinetic product because it came from the more stable carbocation intermediate. This carbocation intermediate here is tertiary allylic carbocation, whereas this carbocation here is primary allylic carbocation. They're both allylic, so we ignore that factor since they both can do resonance. Then we look at the hyperconjugation or substitution factor. Tertiary is more stable than primary, which is why this carbocation is more stable, which would give us the kinetic product. Right. So the kinetic product is going to be that. The thermodynamic product is going to be this right here, where we got these groups here by this oxygen attacking the carbocation there or here, right? Which gives us that or this. After the deprotonation step, because this H here will just get deprotonated by another ethanol and neutralize the alcohol, giving us that right there. So this is the final product after the deprotonation step. So why is it tri? Is it because of the ring? Yes, this double bond here is tri-substituted because there are 3 R groups around it. There is 1, 2, 3 R groups around that double bond, making that a tri-substituted double bond. This is a mono-substituted double bond because there is only 1 R group there. Right? These count as separate R groups right here. So carbocations take precedence over the substituted alkene, right? Carbocations take precedence over the substituted alkene only if we are in kinetic conditions, low temperature. So if we are in low temperature, this is the major product. If we are in high temperature, this is our major product. Right. And he will give you temperature on the arrow. Like this arrow here will have like 70 degrees Celsius or 135 degrees Celsius, 180 degrees Celsius, something like that. But he'll tell you exactly what he wants. Yeah. Mhm. Now we could go over allylic organometallic reagents. Where it's going to be the exact same reaction as in 118A. When we have a halo alkane like that with the bromine, and we put that through Mg ether, that is just going to insert itself between that carbon and bromine, creating your Grignard reagent here. Right. Where before this carbon here was partially positive, but now this carbon right there is now partially negative because the carbon attached to the Mg is negatively charged, making this the nucleophile carbon. Before it was the electrophile, but once we made it the Grignard reagent, it becomes the nucleophile. Right. The exact same thing happens for allylic. Right. Where this is going to be our nucleophile here, the one attached to the Mg, which that nucleophile can attack any electrophile, like anything that's positively charged. For example, that primary halo alkane, it could open up an epoxide. And since this is negatively charged, it would attack the less subside, right? Uh, and at the end of 118B, you also learn about carbonyls, where this carbon right here, that is double bonded to the oxygen, is the one being attacked because that carbon is partially positive. The book introduces it at this part, but I think Pascal will leave it towards the end. But it's the exact same principle. Nucleophile, attack electrophile. Nucleophile, attack electrophile. Nucleophile, attack electrophile. Yes, this is an insertion reaction where this magnesium inserts itself between these 2 atoms, carbon and bromine. Right. Now it's between carbon and bromine right there. insertion. Yeah, same thing here. Okay. Now let's go over the acidity of allylic hydrogens. So let's say we have this alkene right here, and we introduce some kind of strong base. A very strong base that you can see is N-butylide, which looks like a butyl group, 4 carbons, and one of the carbons has a negative charge right there. That's our very strong base right there. When we have a very strong base, right, we have to look for our most acidic hydrogen to deprotonate. And the most acidic hydrogen is going to be the one that gives us the most stable conjugate base. Most acidic hydrogen gives most stable conjugate base. Right. Where whenever we deprotonate a carbon or some kind of acid, it gains a negative charge. So we have to look at which position will give us the more stable negative charge, which is going to be the allylic position here. Because once we grab that hydrogen and make a negative charge on that allylic carbon right there, right, we are going to get this conjugate base right here, that carb anion that is allylic. We know that that carb anion here is stabilized by resonance here, right? So that is the conjugate base of that acid right there. This hydrogen here is more acidic than this hydrogen right there. That's because if we deprotonated that hydrogen, we are going to get this conjugate base right here, where we see that this conjugate base with that negative charge is not stable because it cannot do resonance. There is an sp3 roadblock here that blocks it from doing resonance with the double bond. It's too far away from the double bond. Since it cannot do resonance, it is less stable conjugate base. Less stable conjugate base, meaning that this is less acidic and this is more acidic because more acidic hydrogens gives more stable conjugate bases. Right. Okay. Any questions on the acidity of allylic hydrogens? Okay, so now let's move on to conjugated dienes. So when you see conjugated, think of resonance. When you see diene, think of two alkenes. So there are going to be two alkenes that could do resonance with each other. Conjugated diene. An example of that would be something like this. This is the simplest example of a conjugated diene. Two alkenes that can do resonance with each other. And they could do resonance with each other because all of these atoms here are sp2 hybridized. A network of adjacent sp2 carbons can do resonance, where we can move that double bond there. This double bond can make a lone pair there, giving us this resonance structure here, right? Where since this carbon here lost a bond, that carbon gained a positive charge because it lost the bond. This carbon here gained a lone pair of electrons from that double bond right there, which gives it a negative charge. This checks out because whenever we draw a resonance structure, we have to make sure that charge is conserved. This is neutral. This is also neutral because the charges cancel out. +1 -1 equals 0. Right? Conjugated diene. You could have a diene that is not conjugated. So this is a diene because there are two alkenes, but it is not conjugated because of this sp3 roadblock, blocking resonance, too far away. Not conjugated. No resonance. Right. So because of that, this conjugated diene system is more stable than this diene that cannot do resonance. And the question he might ask is like, which one has more energy? The one that has more energy is the one that is less stable. We said that this is less stable because it cannot do resonance, not conjugated, meaning that it has more energy. This one is more stable because it is conjugated and it could do resonance, meaning that this has less energy. Energy and stability are inversely related. So the more stable a molecule is, the less energy it has, and vice versa. Right. And he might ask it the other way around. He might ask which one is more stable. Then the answer would be this one. If he asks which one has more energy, the answer is this one. Okay. Now, let's say go over how to make them. Preparation of conjugated dienes. So let's say we have this dihaloalkane and we have some kind of strong base like NaOET, ethoxide, and ethanol, right? Let's say we have two equivalents of that or excess. We have a strong base and a good leaving group here. This is a big sign of an, oh yeah, let me scroll up to the NBULI product right here, right? Where what happened in this reaction is that this is the very strong base here, which is going to look for the most acidic hydrogen. And that most acidic hydrogen is going to give us the more stable conjugate base. We have, let's say, these prospects of hydrogens here. Let's say this is A, B, C, D. The most acidic hydrogen is going to be hydrogen C because that hydrogen C will give us the most stable conjugate base. All the other hydrogens, A, B, and D, cannot do resonance if we draw out the conjugate base. If there was a negative charge here, that cannot do resonance. If there was a negative charge here, that cannot do resonance. If there was a negative charge here, which is this case, it cannot do resonance. The only thing that could do resonance is the negative charge here. That is allylic to this double bond here, meaning that it's one away from that double bond. And since it's allylic and can do resonance, that makes this conjugate base more stable, making this hydrogen the most acidic hydrogen here. So this reaction overall is just a acid-base reaction, where the NBULI is the base and the acid is that allylic hydrogen right there. Okay. Now this is E2 reaction. because we have a strong base and good leaving groups. Yeah. And we have two equivalents of it. So let's locate all the beta hydrogens. This is the alpha carbon. This is the beta hydrogen. Alpha carbon, beta hydrogen. If we use one equivalence of the ethoxide, we could grab that beta hydrogen, make a double bond there, kick out that leaving group. That's E2 reaction right there. Right. We have another beta hydrogen here. And since we have two equivalents of it or excess, we could do another E2 reaction, giving us our conjugated diene here. This is a conjugated diene because this diene here can do resonance with each other. Right? They have a network of sp2 carbons. sp2, 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 sp2. Right? So that's one way to make conjugated dienes. Another way is a little bit more tricky. Let's say we have this haloalkene here and a strong base like methoxide. We have a strong base and a good leaving group. Another big sign of E2. But this time we have two different prospects for the beta hydrogen. Right. Yeah. To the product of the above. This one? Yes. Okay. Where this reaction was E2 two times. The first E2 made that first double bond. The second E2 made this second double bond. Okay, now this time we're only gonna do E2 one time, but we have a choice here. We could either grab this beta hydrogen or this beta hydrogen here. Which beta hydrogen do we want to grab to make a conjugated diene? Right. Let's say we grabbed the blue hydrogen, make a double bond there, and kick that out. This is our double bond right here. Right. If we grabbed the purple hydrogen, make a double bond here, kick out that leaving group, we are going to get this double bond right here. Since this is conjugated, this is more stable than this one here because this one is not conjugated. We have sp3 roadblocks here, blocking resonance. Right. So that means that this blue hydrogen here is more acidic than this purple hydrogen because that blue hydrogen gives us the more stable product. Right. Okay. And then from here, you could determine which one has a higher energy, which is this one here, because that one is less stable, meaning that this one is going to have less energy because that one is more stable. Okay, now let's go over the reactions of conjugated dienes, which this is going to go into the thermodynamic and kinetic product a lot. But any questions on what we went over so far? Okay, let's go over the reactions of conjugated dienes now. Where the first one is going to be hydrohalogenation, or the addition of HX. Okay. An example would be something like this. Let's say we have that conjugated diene there, and we put that under HBr. Okay, so you will also see some kind of temperature here, where if you have, again, off of that temperature, high temperature will give you the thermodynamic product. Low temperature will give you the kinetic product. Okay. So there are two alkenes that we could react this HBr with. This alkene and that alkene right there. Let's look at the first alkene, which is reason why they are called thermodynamic and kinetic product. Right. So kinetic product, you could think of it as the one forming the fastest. Because it comes from the more stable intermediate, and the intermediate like exists for a short amount of time. So kinetic, you could think of like speed. Meaning that the kinetic product comes from the more stable intermediate. Thermodynamic, you could think of that as energy, like heat. The thermodynamic product would give us the one with the least amount of energy, or the most stable product, right? Thermodynamic, more stable product. Kinetic, more stable intermediate, where the kinetic product forms first, or the fastest, the first or the fastest product that gets formed. Thermodynamic, it requires more energy, like heat, energy, and some time to get to the most stable product, because it has to overcome that less stable intermediate first, right? Because if we look at an example, let's say we did one here, like this one right here. We said this was a thermodynamic product because it gave us the more stable double bond here, the tri-substituted double bond there. It requires more energy and time to get to this thermodynamic product because it has to go through this less stable intermediate, where the intermediate is the first thing that gets formed. So it has to overcome that intermediate to get that thermodynamic product. But the more stable intermediate here is the kinetic product because that's the first thing that gets formed. It forms faster than the thermodynamic product because it came from the more stable radical intermediate, which gets formed first. Right. Mhm. Okay. Let's focus on this double bond right here. When we react an alkene with HX, we want to form the more stable carbocation, where the more stable carbocation is the most substituted carbon here, meaning that the less substituted side attacks the H, kicks out the Br, and we have that carbocation right here, right? We know that this carbocation here is allylic because it is one away from that double bond right there. And because it is allylic, we could do resonance with that carbocation. where when we draw out its resonance structure, we should have this right here, right? This is the first set of resonance structure that we are going to look into. Let's focus on this other double bond here as well. Instead of that double bond attacking the HBr, let's use this double bond to attack it. This is the more substituted carbon, which means that this less substituted carbon here is going to attack that H, kick out the Br, and give us this more stable carbocation here, right? This carbocation here is also allylic, meaning that it could do resonance with this double bond right here. When we draw out the resonance structure, we get this. Okay, so we have 4 different resonance structures here. Okay, let's classify each one by their substitution of alkene and carbocation. Let's do substitution first of alkene. This is mono-substituted because there's only one R group. This is tri-substituted because there are 3 R groups. This is di-substituted because there are 2 R groups. This is tri-substituted because it is bonded to 3 R groups. Now, let's move on to classifying the carbocations. This carbocation here is tertiary allylic. It is tertiary because it is attached to 3 other carbons and it is on the allylic position, one away from the double bond there. This carbocation here is primary, but it's not only primary, it is primary allylic because it is one away from the double bond there. This double bond here is secondary allylic. This one here, primary allylic. Okay. Now, once we classified all of the substitution of the double bond and the carbocation, we could now determine which one is going to be our thermodynamic product and which one is going to be our kinetic product. The thermodynamic product, we said, gives us the more stable or most substituted double bond, which is going to be either this tri-substituted double bond or that tri-substituted double bond there, right? Where when the Br minus comes back to attack this carbocation, we could have, let's say, these 2 thermodynamic products there. Yeah. Yeah. Yeah, this is chapter 14 content, which Mascal didn't start yet, I think. I think he just finished up chapter 13. I'm not too sure. Right. So let's see. Yeah. Since both of these alkenes here are okay, that's good to know. So I think tomorrow he's gonna start on this content, this chapter 14. Right. Since both of these alkenes are tri-substituted, oh wait, there's supposed to be a extra bond there, right? 1, 2, 3, 1, 2, 3. These 2 could be our potential thermodynamic products. Now, there's only one kinetic product here, and that only one kinetic product is this tertiary allylic intermediate here, because that is the most stable intermediate. It's more stable than the primary allylic, more stable than secondary allylic, more stable than that primary allylic. So this is our kinetic product. This is our thermodynamic product there. Right. Came from the more stable intermediate, gives us the more stable alkene double bond. Okay. Right. Where your kinetic product is favored at low temperature. And Pascal will tell you what that is for him. For thermodynamic product, it is favored at high temperature. High temperature. Right. So on the arrow, you will see some kind of temperature. And then for the product, you will either draw these products or that product there, depending on the temperature. Right. Okay. Now, let's go over another reaction of conjugated dienes. But instead of hydrohalogenation, let's do halogenation, which is the addition of X2. Okay. Okay. So let's say we have this conjugated diene here. This is conjugated because these two alkenes here can do resonance with each other. We notice that these carbons here are sp2 and next to each other. Right. And we could react this with Br2 or Cl2. Let's say we do Br2, CCl4. Okay. There are two alkenes that we could react this Br2 with, this alkene or this alkene right here. Okay. Let's focus on one at a time. Let's focus on this one first. Right. Where the first step of the mechanism is that that carbon attacks the bromine, kicks out the other bromine, and then this bromine here being attacked attacks the other carbon at the same time. And this forms our bromonium ion here. Okay, so you know how back in chapter 12, the Br minus will attack the more subside of the carbocation right away and break open the bromonium ion like that. In this chapter here, that will not happen first. What will happen first is that at the more subside, we are going to break open the ring first by itself, right? The reason why we can do that is because it will form this really stable carbocation right there. That is allylic. It could do resonance with that double bond right there, right? I'm just going to ignore stereochemistry for this reaction because for predicted product, once we have that carbocation right there, now everything is flat and planar. But the Br minus comes in and attack, it could become wedge or dash now, right? So we know that this carbocation here can do resonance with that double bond, giving us this resonance structure here. Right. So these are our resonance structure for this double bond that got reacted with. Now, let's draw in the other set of resonance structures if we used this double bond here. Right, let's do the exact same thing. This carbon attacks the bromine, kicks out the other bromine. That bromine being attacked attacks the other side of the alkene at the same time. We know that we are going to form this bromonium ion ring, where now one bond of this bromonium ion ring is going to break and give us a carbocation. And we want to form the carbocation that is more stable. If we form the carbocation here, that one cannot do resonance. So that is not going to be stable. But if we form the carbocation here, this can do resonance because that is allylic. This is an allylic carbocation. This is not an allylic carbocation. Since this carbocation here is allylic and can do resonance, we want to break open the ring this way. When we do that, we are going to get this intermediate right here with the positive charge there, which is allylic and can do resonance with the double bond right there, right? So this is our other set of resonance structures. Okay. Now from here, let's do the same classification step where we're going to classify the substitution of the double bond and the carbocation substitution. So this double bond right here is di-substituted because there are only two R groups. This double bond here is tri-substituted because there are three double bonds. This double bond here is tri. This double bond here is also tri. Okay. Once we have figured out the substitution of the double bonds, let's now classify the carbocations. This is a tertiary allylic carbocation. This is a secondary allylic carbocation. And this is a secondary allylic. This is a secondary allylic carbocation, right? Now, let's look at which set gave us the more stable carbocation first. This was the first carbocation that gets formed in that set, and this was the first carbocation that gets formed in the other set. We know that the tertiary allylic carbocation is more stable than the secondary allylic carbocation. So this set here is a more stable set than this set, right? I forgot to do this in the last reaction, but since this is a more stable set, we could basically ignore that other set right there. So we're only going to keep into account this set right here. Now we have to determine which one is our thermodynamic product and which one is our kinetic product. This here is our thermodynamic product because it has the more stable double bond. This right here is our kinetic product because it gives us the more stable carbocation. So the kinetic product is when we have the Br minus that got kicked out. It's going to attack that carbocation right there, giving us this kinetic product here, which came from the most stable carbocation intermediate. The thermodynamic product is when we have the Br minus that got kicked out, attacking that carbon right there, which will give us that bromine right there and this bromine right here, where this is the thermodynamic product because this gave us the most stable double bond there, the tri-substituted double bond. Right. And so let's do the same for the last step here. let's look at which set gave us the more stable carbocation first. This was the first carbocation that gets formed. Since this carbocation is more stable than this carbocation right here, we could ignore that set right there. So when I said that could be the thermodynamic product, that is not going to be considered because it's part of the set that is less stable. Where this thermodynamic product here comes from the more stable set and gives us the more stable double bond. The kinetic product here comes from the most stable intermediate right there. So we just ignore the other set by determining the set that is more stable. That gives us the more stable carbocation first. So we only get one thermodynamic product here and one kinetic product here. Same as for this one right here, right? We ignore this set because this set has the less stable intermediates, right? Any questions on this reaction on the thermodynamic kinetic product, on halogenation, hydrohalogenation? Okay. This is the kinetic product. This is the thermodynamic product. And you only draw out one of them depending on what temperature he gives you. If he gives you high temperature, you get thermodynamic. If he gives you low temperature, you get kinetic. Same as for this one. Temperature. Low temp, high temp. Okay. Okay, let's do um two more reactions of this, and then move on to Diels order reaction. Right. So let's say we have questions, no questions. Okay. This conjugated diene right here, and we react that with HCl. So the first thing, make your resonance sets. We have two alkenes here, so I'm gonna react it with, let's say, oh, but we also notice that these alkenes are symmetrical because they have the same R groups. Let me make this a little bit more difficult by making it asymmetrical. Let's say we have that as well. Okay, now let's focus on this alkene first. HCl. We want to form the, okay, this is a tricky one right here. We want to form the more stable carbocation, right? Which is the more substituted double bond side. A lot of people would say this carbocation here is more stable than this one right here. But that's not the case because I'll show you. Right. So let's say we have a carbocation here versus this carbocation right here. This seems like the more stable carbocation because it's more substituted, but this is the more stable one because it could do resonance. It is allylic. This is a secondary allylic carbocation, whereas this is only a tertiary carbocation. This allylic here allows that carbocation to do resonance, which increases its stability. So this is actually the more stable carbocation than this one here because it can do resonance. This one can not do resonance. Right. So since we want this carbon here to have the carbocation, this side now is going to attack the H, the more subside, because we want the carbocation that is allylic. That gives us this carbocation right here. Okay, we could draw its resonance structure now, giving us our first set, which is this right here. Okay, now let's focus on the other double bond here. We want to form the more stable carbocation. They're both equally substituted, but there's one that is allylic and one that is not allylic. This one here is allylic, so we want the carbocation here. That means that the other carbon is going to attack that hydrogen, kick out the Cl, and give us our allylic carbocation here. Once you have this allylic carbocation, let's draw the resonance structure. Right, which gives us that resonance structure here. Okay, now let's eliminate the less stable set. We eliminate that by first looking at the first carbocation that is formed. This is the first carbocation that is formed for that set. This is the other carbocation that is formed in that set. Right, so this is a tertiary allylic carbocation. This is a secondary allylic carbocation. Since this is more stable, we are going to eliminate that set right there because this set came from the more stable carbocation. Right, now let's classify this one. Oh, this one is also tertiary allylic. But now let's do the substitution of the double bond. This double bond here is okay, this is a weird example. Tri substituted. This is also tri substituted. Okay. Right. So I'm getting confused here because this double bond here is tetra substituted. This is tri substituted, where our most stable double bond is this tetra substituted here. But I eliminated that set. And some professors like would keep that set, like in theory, but for Helix, he just gets rid of that set. So I'll have to wait and see what Pascal does. Like if he eliminates a set or keeps it. So I'm getting confused on what he wants here. If he doesn't eliminate it, then this would be our thermodynamic products here. But if he does eliminate it, then both of these could be our thermodynamic product here. I'll get back to you guys on this reaction when he actually does go over it. But for now, I'm confused um on this because different professors have like different rules on this part here. So this is going to be, I'm going to make a note. Let's see. Wait for Pascal to go over this concept reaction because different professor have different rules in determining kinetic versus thermodynamic product. And once he goes over that, I'll have a more clear uh thing on what he wants. Product. Okay. Okay, let's do that was hydrohalogenation. Let's do one example of halogenation and move on to Dios order if we have time or if you guys have any other questions. Right. Let's say we have this and we react that with Br2. Since these alkenes are symmetrical, we don't have to draw two sets. We only have to worry about one set because both sets would be the same. The mechanism would be like this, attack that bromine, kick that out, form the bromonium ion ring here, which is going to be this. Now, this is the different step on this chapter here. We're going to break open the bromonium ion in a way that gives us the more stable carbocation. A lot of people would break it open this way, giving us the tertiary carbocation, because a lot of people would say this is the more stable one, but that's not the more stable carbocation. This is the more stable carbocation because it is allylic and it can do resonance. So we have to break it up this way, not this way, because this is not allylic, whereas this is allylic, which allows the carbocation to do resonance. So the Br is there. Now let's draw in the resonance structure. And we only have to worry about one set because this is symmetrical. Okay. Now, once we have this set, we could determine which one is our thermodynamic product and which one is our kinetic product. This is a di-substituted double bond. This is a tri-substituted double bond. So I could automatically see that this is the thermodynamic product because it gives us the more stable double bond here. Right. Now let's look at the carbocation. This is a secondary allylic carbocation. This is a tertiary allylic carbocation. This right here will give us the kinetic product because it comes from the more stable carbocation intermediate. Now, the Br that got kicked out is just gonna come in and attack the carbocations, right? Where the kinetic product comes from here. And you would draw this product out if you had low temperature on the arrow. And we'll see what Pascal says about that, what the temperature is. If you had high temperature, then you would draw out this thermodynamic product here, which gives us the more stable double bond. Like that. Thermodynamic because we have the more stable double bond. Kinetic product because it came from the more stable carbocation here. Kinetic. What kinetic? There is still a bromine here when I drew out the resonance structure. Bromine, bromine. There we go. Wait. A tip for this is that if you have a conjugated diene and you react it with HX, your product is always going to be an alkene with an X somewhere. But if you react a conjugated diene with X2, you're going to get an alkene with two X's. Since this was X2 here, our product would have two X's, X and X. If we react it with HX, like this right here, we only get one X. Right? Because the H here is attached somewhere in the structure where the H is attached to there, but it's invisible. Right? But the mechanism is the exact same. Or no, not the mechanism, but the principles on the thermodynamic giving you the more stable double bond and the kinetic product coming from the more stable intermediate is the exact same for these reactions here. Right? Okay. See. Any questions on these conjugated diene reactions? Yeah. Okay, I think that was a lot of material. Do you guys want to go over Dio's order reaction? Because let's see. We must go over that tomorrow. Let's see. So we went over conjugated systems, allylic position, carbocation, carbanion, radical, NBS, allylic bromination, mechanism, thermodynamic kinetic product. Uh, these position terms, vinylic, allylic property, like benzylic, so SN1 reactions, organometallic, N-butyl, acid base, conjugated dienes, making conjugated dienes, reactions, addition of HX or X2. Yeah. Yeah. So for the reaction we just did, I can explain how we got to the resonance structures. The reaction we just did. Let's see. This one right here. Okay. So we have this conjugated diene here because we have two alkenes that are conjugated. They could do resonance with each other, reacting with X2, Br2. The mechanism is going to be this, like the first step is going to be the same as the alkene one. One of the double bonds here is going to make a bromonium ion ring here by one of the carbons attacking that bromine, kicking out the other bromine, and at the same time, this bromine attacks the other side of the alkene, making this bromonium ion here, right? Once we have this bromonium ion, this is where the step is different. We are used to seeing the Br minus attacking the side that is the more stable carbocation and kicking it out. But since this is allylic, this is a very good leaving group. Think of it as an SN1-like mechanism. That is just going to leave by itself first and form that carbocation right there. Once we have that stable carbocation right there, that carbocation right there is allylic, meaning that it is one away from the double bond. And we see that this can do resonance by moving this double bond to make a double bond here, which is this resonance structure here, right? Where this carbon here gained the bond, which is why it's now neutral. And this carbon here lost the bond. So that's why that carbon is now positively charged, right? So these are our two resonance structures here. And we know that this resonance structure has the more stable double bond because it is tri-substituted. This resonance structure here has the less stable double bond because it is di-substituted. But this double bond, I mean, this resonance structure here has the more stable carbocation intermediate, whereas this resonance structure here has the less stable carbocation intermediate. And that affects the product of what you are going to draw as the answer, depending on the temperature. If your temperature is high, you are going to draw in the thermodynamic product, which is the more stable double bond product. If your temperature is low on the temperature, on the arrow, you're going to draw in your kinetic product, your more stable carbocation intermediate product. Right? It just depends on the temperature on this arrow here. Yeah. Mm-hmm. Okay. Let's see. I'm going to go over a brief introduction of Diels order because this Diels order thing reaction can get complicated with all the stereochemistry and regiochemistry, but I'll go over that for tomorrow's session in person. But first, let's just introduce what this will do. Okay, the very very basics of it, and I'll go over this again tomorrow with the Diels order. Right. And for this chapter, in my opinion, this reaction is the hardest out of the other reactions in this chapter, Diels order. Right. So you're gonna have your reactants are gonna be what was that called? S cis diene plus a dienophile. That's going to give you a cyclohexene. And I will show you that clearly here. Okay, let's draw in our S-cis diene and our dienophile here. Okay, so this is our S-cis diene because there are two alkenes conjugated to each other. The reason why this is called S-cis because the S-trans version of it kind of looks like an S. And there's another reason why too, but this is how I remember it. This is the S-trans diene. This is the S-cis diene. Right? And this is a dienophile here. When you see dienophile, these things loves dienes, right? Because this file here means lover of. It's a lover of dienes profile, right? So these like that, right? Where dienophile, think of them as the electrophile and think of the diene as the nucleophile. Okay, so okay, this is gonna be a little weird, but this double bond here is going to attack that dienophile. One of the double bonds here is going to attack that carbon, and that double bond is gonna make a double bond right there. I'm gonna number this, let's say 1, 2, 3, 4, 5, 6. We're gonna make a 6-membered ring. Oh, it also might help if I color code these as well. Let's color code that bond pink. Let's make this purple. Let's make this blue. Okay. 6-membered ring right here, where the purple bond is now here. The pink bond is now here. Oh. And the blue bond is now here. And this is our 1, 2, 3, 4, 5, 6 carbon chain like that. Right. Where I moved this pink bond to make a bond between 1 and 6. Before, there was no bond between 1 and 6, but I made that bond between 1 and 6 by moving that pink bond there. There used to be a double bond between 1 and 2, but now that double bond is gone because it made a bond between 1 and 6. There used to be a double bond between 5 and 6, but I moved that double bond to make a bond between 4 and 5, which is that blue bond right there. There used to be a double bond between 3 and 4, but I moved that double bond to make a double bond between 2 and 3, which is that purple bond right there. So this is our cyclohexene products right there. And that is the very, very basics, like the most simple Diels-Alder reaction. It will get more complicated once we have like EDGs, EWGs on it, and like the stereochemistry, endo role, exo role, but we'll go over that all tomorrow. Any questions on this? Right? Where S trans dienes will not work with Diels-Alder. Cannot do Diels-Alder. Cannot do Diels-Alder. Only S-cis diene can do Diels-Alder. Yep. And that might be a conceptual question on a vocab or a multiple choice question. Yeah. And that is it for today. Any questions? Yeah. Okay. So tomorrow, the plan for the content review session is to finish up the Diels-Alder reaction. Yeah. No problem. See you guys. Bye.